Hello, I'm Dave Whitehead, CEO at Schweitzer Engineering Laboratories, and today I'm on the phone with Dr. Greg Zweigle. Greg has a bachelor in physics, a master's in electrical engineering, a master's in physical chemistry, and a PhD in electrical engineering and computer science. Greg, I'm pretty sure your wife is going to cut you off from getting any more degrees, but I guess we can save that for another conversation. While Greg has held a number of positions at SEL, today Greg is a fellow engineer and heads up our wide area power system measurement and control group. Part of Greg's job is rounding up measurements like currents and voltages from across a power system to make an assessment if the power system is in a good state and nothing needs to be done, or maybe it's in a suboptimal state and corrections are needed. One of the tools Greg uses are synchrophasers, and that's the focus of this podcast. So, hi Greg and welcome.
Well, thanks for having me, Dave. It's really great to be here, and this is going to be a fun conversation.
I'm sure it is. It's always fun talking with you, Greg. Let's get started with, what is a synchrophaser and how did it get its name?
Okay, I like this question. The name, it's fancy, but the concept is really simple. We want to control the power system to achieve best reliability and safety, and to do so at the minimal cost to the consumer possible. So in order to control something, we have to measure it first. And I like to think about driving a car. So we use our eyes and our ears to really measure what's happening. We're measuring the system, and the system is what is out there: the cars, the road, the curb, pedestrians. And from there, we control the car with our hands and feet. Okay, so synchrophasers are about measuring. One can think of a synchrophaser measuring system as the eyes and ears of the electric power system. And then for the name, that's not quite as simple. So the word that we use is synchrophaser, and it's not a phaser like on Star Trek. Power system signals have a wave-like shape. So imagine an ocean wave, and engineers use the word phaser to characterize the height and relative position of these waves. So for example, when we say that a power line is 500 kilovolts, we are measuring the height of these waves. That's what we're referring to. For the synchro part of synchrophaser, that's related to the fact that we have to time align these waves. And actually, that was one of the biggest technological challenges related to creating the first synchrophaser measuring systems about 20 years ago.
So stepping back just a second, one of the challenges that we had with measuring the power system, or trying to at least compare measurements across a power system, is that there wasn't time alignment, or you couldn't guarantee a time alignment. So it was a pretty blurry picture. So what was the solution for the time alignment problem?
Yeah. So, when we're talking about controlling a system, most of the systems that engineers try to control are relatively localized. So if we go to the car analogy, you can think about the cruise control in a car, or the controls in an airplane. Even our cell phone has internal controls, and cell phones are pretty small. But on a power system, they span hundreds or thousands of miles. So going to the time alignment issue, to control something of this huge size, we need to make sure all these measurements are aligned at the controller. And that was just a really big problem. In fact, the issue of time alignment, it occupied researchers' minds in the 1980s and the 1990s, and papers were written on, well, wouldn't it be cool if we could do this wide area control? But there was no way to time align all of these high-speed measurements. And the answer came from kind of an unlikely source, which was GPS. So, we're all familiar with GPS. It tells us where we're located. Where am I located right now? Pullman, Washington. So what does that have to do with time? Well, in order to make an accurate location measurement, it turns out we need to keep highly accurate time. So the solution for time alignment was to use the time code portion of a GPS signal, and basically to put an antenna on each measuring device and use that GPS signal for the timestamp of high-speed measurement. So this was really the birth of synchrophaser technologies in about the mid to late 1990s.
Well, that's really cool. But let's step back just for another second. Is the power system is over 100 years old. Can you tell us about about measuring the power system quantities prior to synchrophaser? How exactly was that done, and why wasn't it good enough?
Yeah, that's great. So in the early days, people needed to be at the power system equipment in order to take measurements. So, today, if one of our listeners happens to notice a substation, and there are those fenced off areas with a bunch of silver colored conductors and breakers connected together. And sometimes you'll see in a substation, there's a small building. Today that holds the control electronics. There's no people located at the substation. But in the early days of the power system, people needed to work at a substation. They had to look at a meter or a dial and report that value back via like telephone to someone who would use that information to take a control decision. In the 1960s, a technology called Scada was created. And Scada stands for Supervisory Control and Data Acquisition. Scada was really a major advance for our industry because with Scada measurements, the measurements of the power system were taken automatically and remotely. And from there, they were communicated with whatever telecommunication systems they had at the time. So someone could read a dial in a remote location that was a mirror image of the same dial in the substation. So it was really awesome. And Scada has been with us, in the power industry for 50 years, and it continues to be the dominant method for remote data acquisition. And SEL makes a lot of solutions for Scada systems, as you know. When I joined SEL in 1998, we were just beginning a revolutionary new protection and control system. And at the time, this project was codenamed CFS because one of the microprocessors was a Motorola Coldfire, which was the CF in CFS, and one was the Analog Devices Shark, which was the S in CFS. And I mean, for me, it was a really exciting time to be part of SEL. And Dave, I remember you were the hardware lead on the project, and I was one of the firmware leads, and we put in a lot of overtime back then. I don't know, maybe you have any recollections of those early days on the SEL 421?
There were a lot of long nights, but a lot of fun nights. We were implementing FPGAs and new signal processing techniques, and specifically one of the objectives, actually one of the statements for the product was to put in time-stamped analog quantities so that we could share information precisely down to a few nanoseconds, if you will, between samples in different relays, so we could use this information at higher level processing. And what was that? 20 years ago or so, Greg, we worked on that project.
Yeah. Yes. And that was a great project.
Stepping back real quick, Greg, before I did have
Sure.
one question about the Scada systems and bringing it together. It's not just a new problem, understanding exactly what the power flows are on power systems and using synchrophasers, perhaps part of that. But it used to be you bring in Scada information and you run it through a state estimator to really determine what the voltages and phase angles were across a wide area power system. How has synchrophasers changed that process to really understanding or have some clarity of what's happening on the power system?
Yeah, exactly. So with Scada, because the measurements were taken relatively slowly, we really couldn't get a precise measurement of the state. And as engineers, when we say state, we mean all of the measurements needed for a system in order to be able to predict what it's going to do next. And so with synchrophasers, with these high-speed measurements, we now can directly measure the state instead of having to estimate it. And that's been really an important improvement. So, and actually, that CFS project, it eventually became the SEL 421, which is still really popular today, although we keep improving it. And to do these, we need this measuring device. And so, as you noted, Dave, Dr. Schweitzer, he was one of the early synchrophaser innovators, and he asked us to include that in the 421. Back in the 1990s, there were these standalone devices available to provide synchrophaser measurements. They were called PMUs, which is short for a phaser measurement unit. But they were really expensive and not super reliable. So the SEL 421 really changed all that and made those direct state measurements possible for our industry.
Yeah, and you were really a trailblazer too with doing this. There were no standards, right? There was no guidance on what done looked like for what we refer to now as synchrophasers, right? There was no 37.118 or any of those standards, right? You guys had to invent a lot of stuff on the fly to make all this stuff work. So it's really cool. But taking that a step further is, as engineers, we love, new technologies, inventing new things. Back in 1998 and when we were working on this, were we really solving a new problem, or what is Synchrophasers attempting to address, or what is the killer app for Synchrophasers? Or is it just an academic exercise that goes along with one of your PhDs or master's degrees?
No, that's great. Yeah. I mean, one of the things about SEL that I just love, and it's so important, is that we're always focused on improving the reliability of the power system, improving the safety of the power system, improving the economics. So yes, we always develop new technologies, but to solve a problem, to improve the power system. And the power system has really been changing in the past decade with the significant adoption of intermittent renewables like wind and solar. And the power system has become more decentralized. We hear about microgrids and people using rooftop solar. So we drive by a large wind farm and it's so cool. But I wonder if people realize how challenging it is to get all of these new sources that are weakly controllable at best to actually work together. And it's exciting for us as engineers to work on. And along with that, society continues to increase its dependence on electric power. And why is that? And I like to often remind people that electric power is the safest, it is the cleanest, most reliable, most economical way to move energy from point A to point B. So the power system went from manual measurements in the 1960s and then relatively slow poled Scada measurements, and now to high-speed synchrophaser measurements. You asked about the killer app, and I would really say killer apps, kind of plural, because we are seeing the adoption of high-speed streaming measurements everywhere. And it's really one of the best ways to get all of these renewables working together properly.
Well, that's great. So, you've been working on, in some form or another, synchrophasers for, say the last 20 years. But is this technology being broadly used in power system protection, monitoring, control today, or is it still an academic exercise or a very niche-y technology that perhaps isn't being broadly used, or just really hasn't found its place in power system control?
Yeah, for sure. So, at SEL, we have so many projects that we've done with synchrophasers over the years. I would say in some areas there's a lot of adoption, in some less so. What
would some of those be?
Yeah, so like, for example, there's a great example in Central America, that a problem that we solved for some customers. Central America is about 7 gigawatts, and it's connected to Mexico in the north, which is about a 50 gigawatt system. So keeping that connection between Central America and Mexico is really important to them because it improves the reliability of their system. In the past, they were experiencing these occasionally unstable oscillations. And with synchrophasers, a team of engineers at SEL, they built a system that could detect these oscillations and therefore help the system stay connected longer. There's another example I can think of, a really recent example in the country of Peru. And you'll notice a lot of these projects, of course, are very international, which is great. This technology reaches beyond North America. But in Peru, most of the generation is in the north and most of the load is in the south. And this happens a lot in power systems where the generation and the load aren't together. And there's a couple of 500 kilovolt and 230 kilovolt lines connecting these systems. If they lose one of the high voltage lines, it could lead to a blackout, which is not good. And just a couple of years ago, another team at SEL finished a control system using synchrophasers that could detect and respond to this contingency really fast. And this helps them avoid outages. Although, in some areas, the adoption has been slower. And one case is in the control center, which is the project we have going on now. We could talk about that if you want. But, I think that's where SEL is also helping improve the pace of adoption in many areas.
Yeah, I can actually, you kind of trigger my memory. I remember one project down in Mexico where there was a bunch of generation and there were a handful of high voltage lines taking the power up into Mexico City. And if they were to lose one line, they could still continue to operate with the other line. If they lost both lines, then they'd have some stability problems. And it used to be really complicated knowing which breakers were open, which breakers were closed, and synchrophasers really simplified the whole process, right? Because using that phaser part, they know if two lines were closed, they anticipated what the phase angle between the two remote substations would be. And if they lost one line, the angle would open up a little bit more. And if they lost the second line altogether, the angle got really big. And just looking at the angle difference between substation A and substation B, they could determine if they were going to have a stability problem or not. So synchrophasers really simplified a lot of applications too.
Yeah. The other one I think about that's kind of along those lines is we talk about the wave-like nature of the power system, but there's another wave-like nature, which is what we call small signal modes of the power system. And synchrophasers have really benefited solving some challenges with those oscillations. And I think the best way to think about that, it's kind of fun, is imagine standing at the rotating shaft of a hydroelectric plant. So, and I've stood next to one, and probably you have too. There are these massive steel structures. Above you is a generator, and below, like under several hundred feet of concrete, is water spinning this rotating shaft. And so that spinning shaft is what makes the wave-like shape of the power system signals. It spins, and that's what causes that sinusoidal wave shape. So if we imagine stopping that shaft for a minute and placing a big, fat, wide vertical mark on the shiny surface, and then starting it up again and shining a strobe light at the shaft. And if that strobe light is flashing at the frequency, I'm simplifying things a bit, but generally, if it's flashing at the frequency of the power system, like 60 hertz, then the mark will appear exactly each time the strobe light flashes on this shaft. So you'll see that mark appear for every flash of that strobe light, except in a real system, it won't. That mark will appear to slowly wobble back and forth. And what that is, that's these really large machines swinging back and forth with respect to each other. And because there's a lot of inertia in the power system, and that inertia is coupled by long lines. And so things can kind of start to get unstable, and they can start rocking more and more and more. And eventually that can cause big problems. I mean, this issue has caused outages, major outages in the past. And so synchrophasers, because they're these really high-speed measuring technology, precisely time-aligned over a wide area, we can look at these oscillations. And SEL has developed some solutions around this to be able to control them and prevent outages that could happen if they start to go unstable.
So that's really interesting, because we briefly talked about Scada as this asynchronous slow system, and synchrophasers, depending on how fast you want to receive the message, can be really, really fast. So and Scada is, certainly broadly deployed over just about everybody's power system, where synchrophasers is well, let's say maybe perhaps not as broadly deployed. So how does Scada and synchrophasers, do they fit together? Do they complement each other, or is it something else altogether?
Yeah, that's a great question, because one could think, well, why don't we just speed up Scada? Typically Scada is measuring the power system every 3 or 4 seconds, whereas synchrophaser systems are measuring the power system, say, 10 to 100 times a second. And so it would seem on the surface, well, we could just speed Scada up. But it really has a limitation, which is the fact that it's not time aligned. And that was really a problem, and it's why synchrophasers are kind of taking over, is because even if we sped up Scada processing, it still wouldn't have that time aligned nature. So these applications we're talking about, like these oscillations that can happen on the power systems, or the example you gave where there's an outage if down in Mexico if they lost a line, and there's so many different control systems that SEL has created and is creating with synchrophasers that it's just not possible with Scada solutions, because they don't have that fixed rate, that precise time alignment, and really that ability to look at the power system globally as we design these control solutions.
Cool. Hey, your team has been working with San Diego Gas and Electric on a pretty exciting project. Can you tell us a little bit about it?
Oh, yeah. So The control center is one place where synchrophaser adoption is still kind of gaining momentum. In 2017, San Diego Gas and Electric, they contacted us about a project they called WASA, which stands for Wide Area Situational Awareness. So most utilities have a location where they monitor their entire power system, and that's that control center. And as the name implies, they also take control actions from that site. So one thing to note is that this is where human control actions take place. So previously, we've been talking about automated controls, and that's something a little bit different. So when it comes to the control center, they pretty much all use Scada measurements to populate their displays today for their operators, and for their operators to have what they call situational awareness of the power system. And being a system operator, it's an important job, and it can be really stressful. I mean, it's like an air traffic control center, except instead of guiding airplanes, they guide power flow through an entire city or a state. And in this case, the city of San Diego. For this WASA project, they wanted to bring synchrophasers into the control center. With synchrophasers, we can show the operators a much more detailed view of the inner workings of their power system. And so this lets them integrate more renewables and improve the reliability and the safety. So we are just finishing up the project. It involves all SEL equipment for the synchrophaser measurements. Remember, those are called PMUs. For example, the SEL 421 that we created in '98, that was one of the first. We've had many more different approaches for that over the years too. And it also involves completely new enterprise software for their displays and real-time analytics. So I've got a team of about 2/3 software developers and 1/3 power engineers, and we've been working closely with San Diego Gas and Electric on the project. It's been really exciting, and also, I would say, just like the operators, it's been stressful, but in a good way. Knowing that the city of San Diego is relying on SEL to deliver such an important, large integrated system, and that it has to be 100% perfect when done. It's a big responsibility. So we started developing the enterprise software in late 2017, and we really started from a clean sheet of paper. Software technology has advanced so much in the past 5 years, and our industry a lot of times will improve older software, and oftentimes that's the right approach. But for this new project, we really wanted to start fresh. So the software is web-based, and it's built as a collection of apps and is designed for integration. And one thing I should note is we're talking about synchrophasers, but when we're measuring the power system, we really want all the information we can get. So that's Scada, weather, lightning, maps, topology, and we designed this solution to bring all that together, run real-time analytics, and really help operators make better decisions. So this system at San Diego Gas and Electric, it goes live early next year. And as far as I know, it's going to be the first and only system of its kind worldwide.
That's really cool, Greg. Hey, when we're talking about synchrophasers and Scada kind of gives us, again, this asynchronous, blurry, to use maybe a poor term, a blurry view of the power system. Synchrophasers gives us a really precise view of it, and you're using it to provide new applications and new solutions for, say, the operations folks or control folks in power systems. But I got to believe that Synchrophasers has its limitations. It's probably not the end all be all to every problem that's on the power system. But what are some of the limitations of synchrophasers?
Yeah, that's a great question. Like we talked earlier, synchrophasers are based on that phasor approximation. So we say the power system signals have a wave-like shape, and that's true. And like we mentioned, that's in large part because of those spinning generators that are, they're rotating at that fixed frequency. But this phasor approximation, it's an approximation. The actual shape is a bit more complex, and especially with renewables and inverter coupled devices, the power system is changing. So synchrophasers, while they are a major advance for our industry, they're definitely limited by the fundamental assumption of that the power system waveforms are shaped like a sinusoid.
Yeah, I'd tend to agree with you, right? A phasor, by definition, has a direction and a magnitude. And in our case, this phasor assumes a a uniform sinusoid, right? A 60 hertz signal. So we look at the magnitude and then the angles relative to a reference, this time being time from GPS. We build a very tight bandpass filter around that 60 hertz, and then we throw away all that other information that's out there on the power system. So if you had to ask me, the limitation is this narrow bandpass filter, which it makes a lot of calculations easier for just doing phasers, but there's a lot of information we're foregoing by just using a synchrophaser.
Yes, I agree.
Well, that's exciting. So, hey, given the interesting applications you've described, and also some of the limitations of synchrophasers, obviously being that bandpass narrow look at the power system, what do you see next in this field in time-stamped analog or even digital measurements from around the power system?
Yes, that's the things. Some of the things we're working on now is, instead of sampling at hundreds of samples per second, which is about the rate of synchrophasers, we're at SEL, we're developing systems to go at tens of thousands of samples a second over a wide area, and even millions of samples a second. And all of this time aligned, available for protection, control, analytics. So we're really moving beyond this phaser approximation. I used the analogy of a car earlier, and Dr. Schweitzer likes calling time domain, which is what we're calling these higher rate measurements. He likes saying it's like going from a car to a jet. So it's pretty exciting. And for me, when we're talking about measurements, I think about how this is just like how science continues to advance through more accurate measurements. I mean, from looking through a small microscope and seeing the faint outlines of a cell to modern techniques for rapidly sequencing DNA. And we continue to drive for higher and higher accuracy in measuring our world. And it kind of goes back to what you were saying at the beginning, Dave, like, why are we doing this? I mean, we're not doing it just because we can. We're doing it because these technological advances, going from Scada to synchrophasers and now to time domain, they're really the only way we're going to achieve society's goals for renewable resources. Innovation and technology advances, it's the way we achieve them. And so for me, and I think for all of us, it's a pretty exciting time to be an engineer.
Greg, I'd agree with you. You mentioned a little bit about we increase our sampling rates, and now we're just we're not doing bandpass filtering. Rather, we're following some Nyquist criteria so that we properly low pass filter. But we're sampling the power system over 1 million times per second now, streaming that data to wherever it needs to be. So we certainly have our big data challenges and / opportunities to take new and fresh looks at the power system. I'm amazed when I look at those mega sample per second waveforms, what's really happening on the power system. We just really didn't have any idea or any clue until we started doing this stuff. And then integrating that with the work that you're doing, say, on WASA and other projects, it's to your point, it is really an exciting time to be in the electric power industry right now. There's a lot going on with integration of renewables and changing power systems and distributions and loads and sources and all that fun stuff. So I'd like to thank you, Greg, for coming on the podcast. This was certainly enlightening, and I'm sure we'll have you back to talk about a whole number of other topics, given your wide pedigree and what you know about stuff.
Thank you.
All right. Great talking to you, Greg.
All right. Goodbye.
Thank you for stopping by Schweitzer Drive. Join us again as we learn about, explore, and celebrate electric power. For more information about the show, please visit selinc.com/Schweitzer Drive.